Well, welcome everybody, and thanks for joining us for today's webinar focused on Delaware DOT's 3D Micromodel project. SSTI provided technical assistance to DelDOT for this project to establish a transferable process to perform smart transportation and smart growth analyses through integration of GIS, travel demand, and 3D microsimulation models using readily available industry standard software. The project will create a 3D building library in regionally appropriate styles and give DelDOT the ability to model walking and biking trips and speed scenario analyses to demonstrate the benefits of smart growth policies. The webinar will discuss the rationale behind the project, its benefits, and how its deliverables can be put to use elsewhere. The project has been led by Scott Thompson Graves of Whitman Reckert and Associates, working with Mike DeRoss at DelDOT, and both of them are here joining us and will be explaining the project. Scott Thompson Graves is Vice President at WRA and leads the travel demand modeling, transportation planning, traffic engineering, and transportation and land use studies throughout the company. Scott's a graduate of Purdue University and serves as planning commissioner in the town where he lives. Mike DeRoss has been a planner with Delaware DOT for the last 17 years, primarily responsible for applying travel models to develop traffic forecasts for regional and corridor studies, project design, and conformity. Mike has also worked as an instructor with the University of Delaware for the last 6 years, leading graduate classes in urban transportation planning topics, including 4-step travel models, multimodal capacity analysis, and land development site impact evaluation. Mike holds a master's degree in urban planning from the University of Delaware. As far as questions go for this webinar, please type your questions into the box on the right side of your screen, and we'll go through questions at the end of the presentation. We should have 10 or 15 minutes at the end to go through questions, and we'll answer them then. The recording of this webinar should be available on Monday morning, if not this afternoon, and that'll be available on the SSTI website. That's ssti.us. And please join us for our next webinar, which will be on March 30th, and that'll focus on Colorado's Colorado's Energy Smart Transportation Initiative, which will detail some of the strategies developed with SSTI assistance to incorporate energy efficiency and GHG emissions into transportation planning, increase energy efficiency, and reduce greenhouse gas emissions from transportation, and advance environmentally friendly alternative vehicle and fuel technologies. And you can register for that on the SSTI website at ssti.us. And in April, we'll be holding one on SSTI's school siting project that we're working on with Kansas. But right now, I will pass it over to Scott Thompson Graves and Mike DeRoss to give their presentation, and like I said, we'll handle the questions at the end. Scott, you can take it away.
This is Mike DeRoss from Delaware DOT. I'll start talking first about the background of the project, our goals, how we're going to use this project over the next few years. In getting started, I'd like to thank Eric Sundquist and Bill Holloway, the entire SSTI team. They're doing a lot of interesting things, and this has been an exciting project. We appreciate their help in getting the project to this point. I'd also like to mention Bobby Geyer and Bruce Allen at Delaware DOT. They're working on this project as well, and you may see them at one of the next SSTI conferences. Basically, the goal of the 3D process is to use existing travel demand modeling and traffic forecasting tools in a different way than they've traditionally been used for the past 30 to 40 years. We want to specifically try to evaluate different types of development patterns as part of long-range planning studies for communities and corridors and sub-areas. And we also want to be able to look at some of the smart growth concepts that have been out there and to look at them in a quantitative way so that we can compare trade-offs between locations, form, and design from a traffic and travel demand perspective. We think this will save us a lot of time and money on the scenario development part of most transportation and land use studies. And we also want the process to be easily accessible and easily understandable to a wide range of audiences through the use of GIS and 3D modeling technology. Just very generally, where did this idea come from? Basically, the group that I work in our Department of Transportation is a planning group. We do long-range studies for MPOs. We do traffic forecasting for environmental impact studies. We work with communities and counties to do traffic forecasting components of comprehensive land use plans. And basically, we've been doing this in different variations for the past 3 or 4 years. I'm just going to highlight some of the studies very briefly. I'll probably be rolling through these slides fairly quickly. Just to illustrate why we do this type of detailed travel modeling and to lay the backdrop for some of the shortcomings that these methods have presented to us thus far. And as part of that backdrop, we'll explain why we feel this SSTI 3D modeling process will be so beneficial to us from this point forward as we conduct land use transportation studies. Basically, for all of the traffic modeling work that we do within Delaware, we try to leverage all of our investments so that any feature or new capability that's added to our travel model is part of a legacy process. There's no one-off features. Anything we add so that it's a permanent part of our modeling process, and certainly this SSTI project fits into that as well. Our existing travel models use Cube Voyager and the PTV product Vizoom. Our GIS platform is ArcGIS, and in our shop we use Synchro and the PTV product vSim, which will be used for this process. With this slide, it just kind of illustrates the types of data that we are using to develop these detailed travel demand models. We have detailed shapefile geography on tax parcels, and that's statewide in Delaware. We have a travel demand model that is statewide, and actually it's bigger than our state in terms of its detailed coverage. We have a detailed centerline file, which provides shapefile geography for all roads in the state. Delaware is perhaps a little bit unique in that 90+% of the roads in the state are state streets, including in many cases subdivision streets in neighborhoods and communities. Those are state streets as well, so they're included in our centerline file. And then we also have detailed land cover data in GIS format statewide, and this is done from aerial imagery that's taken every 5 or 6 years, and so we have historical data on that. About 4 years ago, as part of a class at the University of Delaware, we developed a process to basically use tax parcels as the traffic analysis zones for a travel demand model. Most travel models use larger aggregate geographies similar to census geography as the basis for their travel model. In many cases, these traffic zones can have several hundred or even several thousand people aggregated, so the behaviors are very rough representations of actual movements within communities. These more general models are really good at freeways and arterials in terms of developing forecasts. They're good for generating emissions results for transportation conformity, which is an important part of regional planning for MPOs. But they're not necessarily so good for generating the detailed traffic on collectors and local streets that could be needed and would be very helpful in the analysis of specific land use concepts for a particular community. This is what the travel model actually looks like using tax parcel geography as the basis for the model. Essentially, each house is a traffic zone, so we need to come up with demographic data for each of these houses, and we've developed a process for that. And an advantage of this process that we'll talk about in a little bit is that it can be much more intermodal, multimodal than previous models were able to develop. This slide basically shows the types of results we can get. A common output of a travel model is level of service, which essentially compares the volumes to the roadway capacities. We can color code them. This is a pretty typical type of output from a travel model. What's not so typical is the level of detail. Again, we're doing traffic forecasting for all of the streets, all of the roads in a particular community. And this was done initially as part of this, this class about 4 years ago. This is another typical output from that detailed process. Travel models are often used to develop what's called a select link analysis, which essentially tracks all of the origins, all of the destinations on a particular roadway. And if you're talking about a freeway in a typical regional model, you know, that can give you some pretty good information on where folks are traveling on that freeway. What we've done with this slide is to illustrate the thicker red lines to the center left of the slide illustrate the origin-destination patterns for a residential community. So basically, as we exit the residential community, you can get a very detailed depiction in a graphic way of where the destinations for those travelers are. So this is a typical model output that is unique here because we're applying it to such a detailed network. This is a slide from that class as well. It just shows a typical land use concept that would be generated as part of probably any transportation land use study. The triangular area in the center of the slide is a hypothetical development area, and then the blue boxes illustrate different types of land uses, intensity, scales. And basically the goal here was to develop a modeling process where we could analyze each of these land uses as a consistent component of the design and basically do a traffic impact study for this proposed development in the detailed travel model as part of a class presentation. So most transportation studies probably have slides very similar to this. Waiting for the next slide. This is another application of this detailed modeling process. What we did was developed two hypothetical 200-unit single-family subdivisions. The one on the left of the slide is 2 units per acre in a suburban location, and the slide on the part of the slide on the right shows a similar 200-unit subdivision, but because it's in a existing residential community, we're able to provide that density at 5 units per acre. And then we simply run both of those network files in this modeling process and extract the origin destination patterns. What's kind of interesting is that these two hypothetical communities are about 4 miles from each other. So they're generally in the same part of our state, but the suburban community on the left side had about 30% of its daily vehicle miles traveled oriented to a large town located north that was about 15 miles away, and that's the thicker blue line heading towards the top of the slide. On the right side of the slide, you can see that only about 15% of the vehicle miles traveled from this 5 unit per acre 200-unit subdivision were going to that same large town. So because it's located hypothetically within an existing community with more employment opportunities, it actually cuts the VMT down, in this case, by about 40%. Toward the bottom of the slide, you can see the resultant impacts on travel, time, and emissions as well. So this would be a way of using this detailed process to evaluate location of potential residential units. With this slide, what we did was take the 200-unit subdivision within the existing community and simply run it on the left with a single access point, and on the right side we ran the same 200 units with 3 access points, 2 of which were interconnections with adjacent subdivisions. And in running this process and in developing the travel patterns shown by the thicker blue lines, the right side, which is more highly connected travel patterns, appear to be more locally oriented. And I think we would intuitively expect that, but it's helpful as planners and engineers to be able to quantify that, put some numbers behind it, and apply that evaluation to this specific residential location. So the chart in the middle of the slide, the reductions or impacts to VMT and time were not significant, but they were noticeable, and there was a corresponding reduction in emissions as well. We've also applied this detailed process to some statewide planning, and I won't go into a lot of detail here, but what we tried to do at the statewide level was shift about 10% of the projected growth between 2010 and 2040 from the areas in white or gray on the leftmost part of the slide, and we used our existing travel model, which is the more aggregate, larger traffic zones. And what we noticed in doing this effort is that in many cases, because the traffic zones were so large, the 10% shift in projected land use was simply moving from one side of a traffic zone to another. And basically, we were moving 5, 6, 7,000 units in our travel model and not seeing dramatic changes in VMT or emissions, which we thought we would expect to see. And so this became kind of a strong hint to us that we needed to have a much more detailed methodology. So since this study, we've been applying our tax parcel process to larger and larger areas. More recently, last spring, we started a transportation land use study in the northern part of our state. The black polygons were developed as land use concepts. These represent potential subdivisions that could happen within existing zoning, and this would be, again, a sample of a typical land use strategy developed as part of a transportation study. The dotted red line outlines the study area, and in our typical travel model, the dotted red area might comprise 8 to 10 traffic analysis zones. So there's a good chance that all of these potential future units shown here in black would end up in the same traffic zone, or maybe one or two, but it wouldn't necessarily reflect all of the detail that we want to look at with this particular study area. So this slide shows the actual travel model that we developed to examine the land use concepts shown on the previous slide. The red dots illustrate potential residential units that could be developed, in this case, within existing zoning. So it's a full build-out of about 2,000 units. And by placing each of these 2,000 units in the model, we're able to develop a pretty detailed traffic forecast on local roads, collector roads, as well as arterials in this particular study area. And we're also able to evaluate changes in the level of interconnectivity, changes in access points, changes in the job housing balance. Just as a hypothetical scenario, we added some retail jobs within this, and basically we were able to identify the shift or the decrease in home-based shopping trips that would not have to leave the study area and go on a longer distance shopping type trip. So this slide kind of shows where we were about a year ago when we started off on the SSTI process. Looking at a single potential subdivision with this detailed process, this is an existing zoning-based subdivision. It's pretty traditional in its format. Happens to have 5 access points on the existing roadway system. It also happens to have about 40% of its units located on cul-de-sacs, and that's a fairly common or typical range of cul-de-sac units for new construction. And what we wanted to do was to take this exact subdivision concept and evaluate the effect of additional interconnectivity within this same street form. And the darker gray lines illustrate potential interconnections within the same street form, and actually results in 0% of the units now located on cul-de-sacs. And what we were able to identify is that in about half the cases, VMT on the roads which were formerly cul-de-sacs was actually lower with this additional interconnectivity. Using this cul-de-sac as an example, from roughly the midpoint eastward, the traffic did increase compared to the cul-de-sac option, but all the houses that were kind of at the entry point to the cul-de-sac actually showed a decrease in VMT. And we found that pretty much in every case. So again, basically it's an intuitive outcome, but in this case we were able to quantify it, put some numbers to it, and actually show the effects on traffic and travel of some relatively small interconnections within an existing subdivision. This is our latest iteration of the tax parcel modeling approach. We're using it to examine a transportation investment district, which is the area inside the dashed red line. Basically, each of the dots inside the dashed red line illustrates an existing housing unit, a recent subdivision that's been built, or a recent subdivision that has been recorded but not built to date. So it's existing land use capacity. And what we want to do with the tax parcel method, especially the SSTI process that we're working on right now and talking about today, is to use the SSTI process to help us fill in the larger white areas, which are existing unbuilt land. We have an idea of the units that could be built in those areas, but developing this type of an approach is a little bit tedious, takes some time. Just within the dashed red line, there's about 4,700 traffic zones. The typical regional model usually has 1,000 to 2,000 traffic zones. There's some out there that are 3,000 or 4,000, but in this case, we're basically taking about a third of an existing traffic zone and adding almost 5,000 traffic zones inside that one area. So it's a significant increase in the level of detail, but one of the catches is that it's time-consuming to actually develop this model. To actually do the coding is a fairly significant effort. It does allow us a very powerful tool to be able to evaluate interconnections, changes in form, changes in density, but those benefits are only realized after we've invested the time to do the coding. So with this SSTI project, we hope to speed that up. So kind of the lessons that we've learned in using this detailed approach for the past 3 or 4 years. The advantages on the left side, it's a high level of detail that allows us to look at subdivision form and interconnectivity, which are pretty common themes in the smart growth community. Gives us very high resolution traffic data, which can potentially support microsimulation. We'll show a sample of that in a little bit. It allows us to take our existing statewide travel model and using that geographic coverage of statewide travel patterns, look at actual policy options such as land use shifts, different roadway concepts, and the real advantage of it so far is the ability to generate multiple scenarios, looking at ranges of land use density, again different forms, and to look at those in a detailed way. Some of the challenges that we've encountered, basically it's long coding times. We're talking several weeks in some cases of developing these detailed travel models. There have been some improvements in using GIS routines to help speed that up. Because of the long coding times, thus far we've only been able to look at a relatively small number of scenarios. And because there's so many traffic zones, it can involve some fairly long modeling run times. So kind of the basis of our project with SSTI right now is there a better way that we could link existing travel models to look at these detailed problems and give us more quantitative data and can that actually work? Oops, that's not good. Oh. Thanks. This slide basically illustrates how we want to use this SSTI process in terms of the typical transportation land use study that we would do in our state. Typical study would try to look at the effects of different types of residential growth, mixed-use development, and just illustrating the range that's out there, you know, rural to traditional suburban, with 40–50% of the units on cul-de-sacs, neo-traditional design, a little bit tighter, compact form, possibly some mixed land uses, versus a smart growth, which typically would comprise higher density and some locally oriented non-residential land uses as well. So we want to be able to use this SSTI modeling process to set up this range of scenarios in a fairly quick way, and to be able to return the results of the model to the public, to the working groups, again, in a relatively quicker process than we've been able to do thus far. So one of the main goals of this SSTI project is to develop a process to quickly evaluate landforms, accessibility, and potential effects on travel across a range of community design standards. There's several components to that within a travel model. On the left side, we will obviously need to come up with some assumptions on land use density, intensity, different form-based standards, possibly some pattern book type regulations. We obviously need to have some assumptions on accessibility as it relates to the connectivity ratio of the number of streets versus the number of intersections within a potential or hypothetical residential community. We definitely want the process to be multimodal and able to look at bike, peds, and transit as well. On the travel model side of this process, we have or are getting information on trip rates, trip lengths, trip purposes that is needed at the household level to generate traffic forecasts for each of these tax parcel-based traffic zones. The data on the right side is fairly common in travel modeling. Typical outputs are volumes, levels of service, emissions, greenhouse gases, energy consumption, but again, they're usually generated in fairly large traffic zones. It's aggregated behaviors of several hundred or several thousand people. So it takes a pretty big change to illustrate some shifts within that larger geography. So we're developing some interfaces that Scott will demonstrate in just a few slides. It needs to be a single process for us because to us that's where the time advantage is going to come from. So we want to leverage existing functionality within our travel model software, the Cube Voyager, as well as existing ArcGIS plugins and toolboxes. We think that this will reduce the scenario development time, and by taking that from weeks down to a few days, or in some cases many days down to just a few days, that's where we can really gain some ground in terms of using travel models more frequently to look at a more detailed type of land use and transportation analysis. And we're also hoping, because it's in GIS, that it's able to facilitate generation of multiple scenarios. So in the past, when we were looking at 2 or 3 scenarios, now in less time, we can actually look at 2 or 3 times that number of scenarios. And we also want to be able to leverage existing GIS data that we have related to land covers, land use, zoning, and things like that to help us assemble our scenarios. One important feature that we are building into this SSTI process is microsimulation. Again, as we mentioned, most states, most MPOs have a travel model. They tend to not lend themselves that well, in many cases, to public involvement processes. They're not that highly visual, although they are certainly becoming more so with recent advances. But we want to be able to have this detailed travel modeling process at the tax parcel level integrate effectively and seamlessly with existing microsimulation tools, primarily as a public involvement technique, but also because these microsimulation tools can generate very detailed measures of effectiveness that we're simply not able to get out of a traditional traffic model. We also want this detailed microsimulation process to use local vernacular architecture that's more common to the East Coast. Nothing against other types of architectural styles. They're very very appropriate for their communities. But when we go out to the public, we want to be able to showcase to them potential land uses in a way that they probably will see over the next 10 to 20 years. And so we will need locally appropriate 3D models to help us do that. And this is basically an overview of the process that we've been working on for the past few months with SSTI. On the left side in the yellow box is basically our land use generator process. And that is something that resides within our typical cube model. The 3D image library and the GIS routines using ARC attached to that subdivision model, and then we can push both of those things to our travel model, or if we need to take that optional step, we can go to the microsimulation in the green box at the bottom. And we're also looking at adding 3D printing to this process, again, just as another way to showcase the results in a detailed way to the general public. Basically, what we expect is that the travel model part of this we will use fairly often, and that the microsimulation part of this we will only use in those cases where we think that that extra effort invested in the 3D simulation will help us on the analysis or with the public involvement. And this is just a screenshot of our 3D model that we've done so far. This is a screenshot of a 3D printing process output, and so we're hoping that a tool like this will definitely help us convey to our communities some of the results of our analysis. And with this slide, we were trying to illustrate that the SSTI process that we're working on right now, shown by this red box, we're going to wrap that up in the next few months. We're then going to continue working on it by refining it with additional detailed data on bike and ped modes. We have a couple applications of this process that are in the pipeline, and I just wanted to showcase this as being part of our array of modeling tools that we use on our planning studies. So with that, that's the background of how we got to where we're at today. And Scott will now demonstrate some of the steps that we've developed so far.
Thanks, Mike. As you said, there's a tremendous need in our industry for a process such as this that streamlines the analysis and also the conveyance of information to the public. One of the first questions that we had to answer when we got into this is, why go with a parcel-based approach, and can you get the same information with a lesser level of detail? So back to a 200-unit subdivision, we did a case study. What happens with a suburban location and an urban location, and what happens with a cul-de-sac style development in the suburbs versus a grid style in the suburbs, and then an urban development that had a cul-de-sac style versus a grid style. So to answer that question, we looked at 3 different models. One was the regional peninsula model, which covers the entire state of Delaware and Maryland's eastern shore with 2,000 traffic zones. We determined we looked at what would happen if we went with a census block approach that took that 2,000 zones and increased it to about 20,000 zones, and that was the original micromodel that we came up with. And then we determined, or we evaluated what would happen if we evaluated that individual subdivision that we were looking at using parcel-based approach. As you can see, the suburban locations shown in blue and red all produced about the same results regardless of the level of detail we looked at. However, as we added detail to the analysis zones in the geographic areas we were looking at and got down to the parcel area, it showed a bigger disparity between average trip lengths from a subdivision in a suburban location versus an urban location. Once again, when we looked at the number of walking trips that were generated, neither the peninsula model approach with 2,000 zones or the 20,000 zone approach statewide provided a sufficient level of detail to show any difference in the number of walking trips, regardless of where or what urban form the development pattern took place. However, when we used the parcel-based model, there was a significant difference between the number of walking trips that the suburban subdivisions produced versus the urban subdivisions. And also there was a significant difference shown between the green line and the purple line between a grid pattern and a cul-de-sac pattern. We also wanted to highlight some project success stories of projects that we worked on prior to the SSTI process being developed and come to fruition, but would have certainly been enhanced and certainly would have produced faster results once SSTI was produced. With that, we wanted to show an example of what the VSIM simulation would look like that Mike had mentioned earlier. Bill, are you able to click on the? Okay. There we go. So what we have here is a proposed roundabout project in a small town in southwestern Pennsylvania named Rochester, Pennsylvania. When a roundabout was proposed, this was going to be the first roundabout in the area. There was a lot of public consternation when we approached them with typical information, level of service maps, and design drawings, basically. However, when we showed them the complex project in a 3D simulation, they immediately bought into the process and stopped resisting the proposal. And actually went from being, advocates against the project to being major supporters for the project. Another case study would be the US 6N Transportation and Land Use Study, which was done in northwestern Pennsylvania in Erie County. The problem that they'd run into with prior similar studies in the area is that they never provided really concrete answers or information. So folks went in there and tried to advocate smart growth and smart transportation, but the locals really didn't buy into it. So the study that was done needed to really provide hard programmable solutions, and it needed to balance the needs of a growing township with an interchange access to a built-out small town, which in Pennsylvania we refer to as a borough, that kind of bear the brunt of traffic congestion but didn't gain the benefits of increased tax base. Using this type of approach that SSTI would enhance, we were able to actually gain buy-in. The original proposal in order to solve the operational problems was actually a 5-lane roadway on 6N. But by using a detailed model and microsimulation, we were able to gain buy-in and support for a set of land use regulations, access regulations, and basically building out the grid system and surrounding roadways in a better manner, and recommend a 3-lane alternative on US 6N, which was unanimously supported by all the stakeholders. So basically, by using a process that we're recommending here and discussing today, we were able to gain buy-in and support from the working group stakeholders and the public, which was very contentious. We were able to perform a true smart transportation analysis with a limited budget, and all the recommended land use ordinances that we came up with were actually adopted by the locals. Now that's a pretty powerful message, because I know in Pennsylvania and in Delaware and in most of the states that I work in, local jurisdictions own the land use regulations, not the state. And so it's really hard for us to come in there with a straight face and ask them to do things differently. They look at us like we're selling snake oil. However, what we found was when we present them with the right information, we can gain buy-in and support. Similar things happened when we did the 19 corridor study, which is the success story number 3 in west central Pennsylvania. They had a lack of pedestrian connectivity, traffic congestion, and economic development was a problem. Cabela's Sporting Goods store, which is a major regional sporting goods store, had actually approached the rural township about building their proposed facility adjacent to their interchange in the southern portion of their township. They denied the application and said, you would actually just ruin the quality of life of our communities if you built here. A few years later, they had a lot of buyer's remorse when they saw that same development occur in West Virginia, and they saw all the benefits to the community's tax base where that was located. So they approached us and said, how can we grow but still maintain our quality of life? Using advanced modeling and a combination of regional modeling like Mike discussed and then microsimulation modeling, we're able to quantify that by making a few simple additional sidewalk connections adjacent to the borough. For example, connecting to a grocery store that was less than half a mile from the borough boundary, and a Dairy Queen that was less than half a mile from the borough boundary, and better connections to the elementary school. We were actually able to reduce automobile traffic congestion in the afternoon rush hour by about 10%. We were also able to rapidly to evaluate 4 different land use scenarios: a low growth scenario, a moderate growth scenario, high growth scenario with and without smart growth, and then a build out scenario. The important thing is to keep in mind, we were talking to a rural township who were not large advocates of strong zoning ordinances. However, using this approach and quantifying the benefits of multimodal investments and actually showing them with 3D microsimulations the results of different land use policies, we were actually able to gain buy-in and endorsement for smart growth policies and multimodal investments, which was extremely successful for a study such as that. And we got buy-in from the township and the borough. So the message there is that this process can really lead some concrete positive results when used wisely. The nice thing is, once this SSTI project is done, and we appreciate working with Mike at DelDOT and with SSTI to allow us to assist them in this project, is that we would have probably reduced the scenario analysis time for those 3 success studies that I just mentioned by about 50 to 75%, which would allow us to either come in much less under budget or evaluate more alternatives, whichever was required. So where we are in the overall process for SSTI is the GIS process is developed, and we're working on refining the graphical user interface. We refined the travel demand model process to automatically accept the information from GIS, and we're working on streamlining the process to get information from both GIS and the regional model in an automated process into the microsimulation. So if you think about accessibility to these types of models as a pyramid, the majority of our field of transportation planners can easily use GIS or graphical user or GIS tools. That's very widely used throughout the process and throughout our industry. Travel demand modeling is done by a significantly smaller portion of the population that loves math and statistics. And microsimulation and high-end microsimulation with 3D elements is also done by a smaller portion of the populace. So what we're hoping to accomplish by the SSTI process is allow a lot of the scenario development to be able to easily be done by a larger portion of our population. That'll make it much more likely that we're able to evaluate multiple scenarios and things like that. So it'll be quite powerful once we're done with it. So currently the GIS process operates pretty straightforward. You open up the screen, open up your shape files, and load the GIS application. Next, you identify the region or the growth areas that you want to evaluate and specify proposed densities. You can specify different densities for different areas within one open application. You can use those densities, for example, 2 houses per acre or 4 houses per acre, to help you estimate how many roadways you'll need to support that development. Once the roadways are sketched into GIS, you're prompted to select a different housing, or the different housing types that you'd like to apply to the roadways. So you identify the roadway that you'd like to select, identify whether you want the new houses to occur on the right side of the roadway, the left side of the roadway, or both sides of the roadway. You can either use default spacing based upon your densities for frontage roads, or frontage, the distance between driveways, and also setbacks, which is the distance between the curb and the front of the house, whether you're going to use a smart growth or a traditional growth style of development. And you also have the ability to customize the frontages and the setbacks. Once you've identified all of that information for a given roadway, the procedure will automatically locate the houses along the roadway, gives you the option of whether you'd like to delete or remove houses if you need to make them look appropriate. Once that's done for all the roadways in the study area, you're prompted with a question of, are you satisfied with it? And if you are, it'll automatically update your regional travel demand model network, save the demographic parameters that you'll need to work with the travel demand model, and you're ready to go. The process literally can occur pretty close to the amount of time it took me to walk you through that, especially the more comfortable you get with it. So rather than taking days or weeks to code a scenario, it's something you can easily code multiple scenarios in a given day. So it really should streamline the process. Once you're done with that, you can also flip it over. If you have 3D Analyst in ArcGIS, you can look at the subdivision in 3D, which this is a view of what that process would look like. It's the same subdivision we just looked at. And here's a closer in view, so you can see immediately, and we're working on refining and adding additional housing styles and color schemes, but this is a product you could easily take out to the public to explain what different densities and different landforms would actually look like on the street once they're built. So in addition to looking good, it actually refines the process of coding these scenarios in your regional model. And this is the same subdivision and what it would look like in a regional model, which, as you can immediately see, is not as exciting as the 3D view was. We've also modified the statewide travel demand models processes to easily receive this information. That required changes to the trip generation step, the trip distribution step, the mode choice step to be able to better accommodate and account for bicycle trips, pedestrian trips, travel demand management strategies, and whatnot. And then the traffic assignment, which actually loads the projected traffic onto the network. So all those modifications have been made to the regional model. We're able to then extract the sub-area from the model, which is basically take the entire state of Delaware on the eastern shore, highlight a smaller select portion of that model. We can then export that to a format that the microsimulation model, in this case VSIM, can read and begin to use for the 3D simulation analysis. This is an example of the Cube Voyager scripts and some of the changes that we've made to the regional model. And we've also come up with a demographic synthesis process within the model to be able to assign the appropriate level of population, employment, households, and automobile ownership to each of the houses within a given subdivision. So, as you can see, the SSTI model really enhances existing tools to help any user, whether it's a metropolitan planning organization, a state organization, or a consultant, to evaluate smart growth and smart transportation strategies in a much more streamlined fashion. Like I said, it would be great to be able to allow urban planners or community planners who routinely don't use travel models to be able to provide the inputs that we need to evaluate. It then allows us, analysts that usually use the travel demand models to produce the information that the public needs to understand things. It also saves time and money for transportation and land use studies and scenario analysis. It'll either allow you to do it less expensively or evaluate more scenarios. And then it produces results that are really easily accessible to all audiences. Using the example earlier of the Rochester roundabout and the simulation processes that we've used for other studies, we found it's really easy to explain things to folks when you show them a nice moving picture of what the results of different decisions would be on their, on their future. And with that, we'd like to thank everybody for attending today and open it up to any questions.
All right. Thank you, Scott and Mike. Really appreciate that. It's interesting. So we have time to take some questions here. Anybody who's got additional questions, please let us know. Type them into the box on the right-hand side of your screen. So, Scott, would this process then, what would another, say an MPO or a state, what would they have to have already, what would they already have to be using in order to bring in this SSTI process and get it running? Would they already have to be using Cube and ArcGIS and any other software?
Well, at a minimum, they would need to use ArcGIS, which is probably the most common GIS package in the country. The general process would work with any of the major travel demand model packages, whether that's, Visum or Cube or, Transcat. It would also work skipping the step with a regional travel demand model and just helping you populate VSIM or microsimulation processes with buildings and roadways. You could easily work that way as well. So it's fairly transferable. So the goal would be that folks would be able to use their existing equipment, make minor or their existing software, make minor enhancements, and be able to use the process easily.
Great. And we've got another question. Would this tool allow easy visualization of the effect of increased transit or bicycle traffic with the same trip volume?
Yes, it would be able to actually quantify or calculate the mode shifts. So if you would double the transit frequency on a transit route, it would be able to calculate how many less automobile trips and how many more transit trips you would have. It would show more frequent buses. It would also show the increase in pedestrian volumes if you added pedestrian enhancements. For example, if the community doesn't have sidewalks and you add them, it would help you estimate the pedestrian volumes and then actually visualize that pedestrian flow and the reductions in automobile traffic.
That's great. So you've got bicycles and pedestrians that can be added into these little videos that you can make?
Yeah, we do that constantly.
Great. Somebody else asked whether these slides will be available after the webinar, and I just want to reiterate that, yeah, we'll have the recorded video of this webinar, which will be available on the SSTI website, and that's ssti.us. They should be available either later this afternoon or on Monday. Let's see, another question here. I'm wondering, have you seen a difference in how receptive communities are to changing their plans, say reducing the number of cul-de-sacs, when you just show them the numbers? I guess the question is, what is the difference between just showing a community the difference in traffic volumes on nearby roads as a result of having a more connected network versus having that video to show them? What do you think is the, how much of an added benefit do you think it is having that 3D visualization?
I think the 3D is pretty important. The travel model part of it is useful to explain to folks what the impacts might be in a particular community. In many cases, we're trying to explain to them the advantages of interconnectivity and to try to put some numbers to that, how much quicker they might get to shopping or school opportunities, or how much quicker emergency response times might be with some additional interconnectivity. So I think the numbers are part of it, but certainly the 3D is an effective tool generally, especially if you can back it up with some actual traffic forecasts that are from a modeling process.
I'd agree with Mike. We have, when we've presented in the past static images of traffic volumes or traffic flow, those are sometimes esoteric and people have a hard time attributing to how that'll affect their everyday life, even if you say, hey, it's a level of service A versus C or D or E. However, as soon as we show them the simulation, we almost immediately get buy-in and support for smarter growth strategies.
All right. And you mentioned that you foresee that planners could be coming up with some of these scenarios And do you think that it would be the situation where you could have planners coming up with the scenarios and then they would transmit those scenarios to a modeler, or do you think it could that planners could actually take it from start to finish themselves?
Well, I guess it's hard to assert the skill sets of other planners. Okay. I know our planning folks and modeling folks and microsim folks, we all sit in the same shop and share a lot of work. But I could easily see a process being streamlined to the point where they would a general planner and general practitioner would be able to come up with a scenario in GIS and execute it in the regional model. The microsimulation part can get a little cumbersome. Mm-hmm. But the with the streamlining, they would at least be able to assist in that as far as laying the groundwork, getting the houses in the right locations and the commercial developments in the right locations.
Right.
Bill, this is
yeah.
Mike.
Go ahead, Mike.
I think if we don't get this to a lot of planners, we've missed our target a little bit. I mean, I'm a planner, but I work with models. Do I know everything that's going on inside the model? No. But I know enough to be able to explain it to the general public, to agency management, and to other planners. So I think getting this to as wide an audience as possible is certainly one of our goals.
Great. And we got another question here. What is the level of effort in revising Cube and Vism when you add new links or origins and destinations? Origin-destination pairs, that is.
Well, I've been working with Mike long enough that the answer is going to be easy and complex. It's complex because Mike won't let me just do it, but it's easy because he asks us to basically refine his process to make it easy in the future. So our goal with working with Mike is we've refined his model so that nothing needs to be changed within the regional model in order to evaluate a scenario using the SSTI process. So once the new network is exported from GIS, we don't have to do anything. You just attach it to Cube and run it.
All right. And then that holds true also for the visualization piece, that just flows pretty smoothly then once you've done your created your scenario and fed it into Cube, then you can model that relatively easily then after that.
Taking it to the microsimulation is a harder process because the microsimulation software isn't set up for scenario evaluation in the same way that regional models are. But as far as showing it and having things pop in correctly, yeah, that is a much more streamlined process.
All right. Well, I guess that is, we've reached about the end of our time today. I want to thank both of our presenters, Mike DeRoss and Scott Thompson-Graves. We're looking forward to the completion of this project and getting it out there for use. It looks like it'll be a big help. So thanks again, folks, and you can get the recording of this webinar on the SSTI website by Monday, definitely, and join us on March 30th for our webinar on the Colorado Energy Smart Transportation Initiative, which is another SSTI technical assistance project. Thanks a lot, folks. Have a good weekend. Bye-bye.